Hello and welcome to Maths Online Academy. Today we have physics and we want to discuss thermal expansivity. Thermal expansivity is talking about how the length, area or volume of an object changes due to change in temperature. It is a common occurrence that when we apply temperature or when we heat an object, normally the object will expand, whether it is solid, liquid or gas. When we apply temperature or heat it, the object will normally expand or increase. It will increase either in length or volume or area. This is what we call thermal expansivity. Expansion that is brought about by increase or change in temperature. When you have your rubber band and you stretch it, the length will increase, but it is not a thermal expansivity because you are just stretching it. It is not increase in temperature or change in temperature that is bringing about the increase in length. When you apply temperature to bring about increase in the length of the object, we call it thermal expansivity or thermal expansion. This means that expansion can occur in different ways. You can either stretch something and get it expanded. This one is not a thermal expansion. But when you apply heat and the object gets expanded, we call it a thermal expansivity. So that is the difference between thermal expansivity and other expansivity or other expansion. In thermal expansivity, heat must be involved. It is heat that brings about the increase in length, area or volume of the objects. That is what we call thermal expansivity. Thermal expansivity is of three types. We have linear expansivity, we have area expansivity, and we have volume expansivity. 1. Linear expansivity. Linear expansivity. Expansivity or expansion. We have area expansion or area expansivity, and we have volume expansivity. Volume expansivity is also called cubic expansivity. Cubic expansivity. So linear expansivity, area expansivity, and volume or cubic expansivity. What is the difference between these three things? Linear expansivity is talking about the increase in length of an object due to change in temperature or due to an increase in temperature. It is length that is increasing in linear expansivity. In area expansivity, we are talking about increase in the area of an object due to increase in temperature. That is, when you increase the temperature of an object and it brings about increase in the area of the object, we call it area expansivity. While volume or cubic expansivity is talking about change in volume or increase in volume due to increase in temperature of the objects. Linear expansivity is denoted with the symbol alpha. This is linear expansivity. Area expansivity is denoted with the symbol beta for area, while cubic expansivity is denoted with the symbol gamma. This is for cubic or volume expansivity. Cubic or volume expansivity. Both area, linear, and volume expansivity are all measured. The unit of them is per Kelvin. They have a single unit and the unit is per Kelvin. Both linear expansivity, area expansivity, and cubic expansivity. The unit for all of them is per Kelvin. Now the formulas, the mathematical expression for linear expansivity is this. For linear expansivity, that is alpha, the formula is, we say that it is change in length of an object as a result of change in temperature. So it is saying that the change in area, the change in length is proportional to change in temperature. The formula actually gives us, this is change in length, or let me use this to denote change in length. Change in length all over change in temperature times the original length times original length. The original length. Now this gives us, assuming we have L1 as the initial length of the object before you hit it, initial length, and you have L2 as the final length of the object, that is after hitting it, the length of the object increases to L2 final. Now, and we have T1 as the temperature of the object before you hit it, initial temperature, and then T2 as the temperature of the object after you've heated it, final temperature. Now the formula or the expression for linear expansivity is now telling us that linear expansivity is equal to change in length is now L2, that is the final length, minus the initial length, L2 minus L1 over change in temperature is final temperature over initial temperature, which is now T2 minus T1, everything times L1, where L1 is the original or the initial length. So this is the formula for linear expansivity, and I said that the unit of linear expansivity is per Kelvin. Now for area expansivity, just like in linear expansivity, we get it as the change in area over change in temperature times the original area. So we are going to have, assuming that we denote area with A, Let's say that the initial area is A1, initial area. Then we have A2 as final area, then T1 as initial temperature, and T2 as final temperature. Then we are going to have that beta is equal to alpha 2 A2 is equal to A2 minus A1, that is final area minus initial area, over brackets final temperature minus initial temperature, then times initial area. So this is the formula for area expansivity, and the unit again is in Kelvin. Then for cubic expansivity, it is the change in volume over change in temperature times the original volume. If you use V1 to represent the initial volume, initial, V2 final, T1 initial temperature, and T2 as final temperature, then we are going to have that gamma, which is the volume expansivity or cubic expansivity, is equal to change in volume, which is V2 minus V1, over change in temperature, which is T2 minus T1, times by the original volume, which is V1, that is the initial volume. And again, the unit of gamma or cubic expansivity is per Kelvin. So these are the formulas for linear expansivity, area expansivity, and cubic expansivity. Now this expansivity, we see it every day in everyday life. The effects of it are seen in electrical transmission. Sometimes if you come to a place where electrical installation is done newly, overhead wire passing through poles, the wires will be very, very tight at the initial time, but after some time, like some years, you see the wire sagging, coming down, drawing down. That is because the wire is copper, is iron. After some time, as heat is touching it, after some time the iron or the copper will begin to expand. As they are expanding, they will be sagging. Their length will increase, and then the extra length will be sagging down. So that's why you see electrical wires, sometimes they will be sagging down or being somehow loose, unlike the way they were before or during the initial installation of the electrical wire. That is a bad effect of expansion. Also, in bridge construction, when bridges are constructed, they give some room for expansion, because if you don't give room for expansion, the metals used in constructing the bridge, sometimes it will begin to expand, and then the bridge will begin to damage. That's why they put small gap in a bridge, so that when the bridge is now expanding, they will come together, and on normal distance they will remain the same. So that is another effect of expansion. There are so many other effects of expansion. Also, when we have maybe you have your cork, sometimes it is very difficult for us to cork a bottle. If you have a wine that is corked with a wooden cork, sometimes for you to remove the cork, it will be very difficult for you to do that. What you do is that you put the bottle inside a hot or warm water. The bottle will expand, and then you'll be able to bring out the cork. When it expands, the opening of the bottle will become loose, and then you'll be able to bring out the cork easily. That is a good effect of expansion. When we lose expansion for good, it is used in a good way, using it to bring out cork from a bottle. We also use expansion in we also use it in the construction of iron, electrical iron, electric iron. There's something we call bimetallic strip. The bimetallic strip, it changes shape as it expands. We put it in electric iron. When the iron is heated too much, it will change its shape, and as it changes its shape, it will move away from the connection. It will disconnect itself from the electrical source, and so the heat will start coming down. Now when it contracts, when the heat of the iron becomes too low, the contact will come back again, and then the iron will start heating up again. So that is another good use of expansion. Another good use of expansion is in construction of a thermostat. The same principle that is used in iron is also used in construction of a thermostat. So these are the ways we can use expansion, or where expansion can be of benefit to us, and in the other way where it can be of bad use to us. Now let's look at some examples of expansion. Let me solve this example. Here we have that example 1. Now let me just say this. Please notice that area expansion or area expansivity beta is equal to 2 alpha, and gamma is equal to 3 alpha. That means that if there is any equation given to you and you are able to calculate the area expansivity in the equation, you can calculate if you're able to calculate the linear expansivity, you can calculate the area expansivity by multiplying whatever you get by 2. You will get the area expansivity. And if you want to get the volume expansivity for it, you times it by 3. Area expansivity is equal to 2 times linear expansivity, while cubic expansivity is 3 times area expansivity. Now let me look at some examples. Example 1. Example 1. In the construction of a bridge, construction of a bridge an iron rod of length 3 meter was used. When the ion is heated, when the ion is heated from when the ion is heated from 29 degrees Celsius to 41 degrees Celsius, its length expanded. Calculate the increase in length. Calculate the increase in length. Calculate the increase or the new calculate the new length of the ion. The new length of the ion if its linear expansion linear expansivity is if its linear expansivity is 1 times 0 times by 10 raised to power minus 5 per Kelvin. Now, for us to solve it, solution, we bring out our parameters. The parameters given to us, we have the initial length of the ion is equal to 3 meters. The initial length is an iron rod of 3 meters. So when the ion is heated from 29, so this 29 is the initial temperature to final temperature of 41. Okay, so T1 is equal to 29, T2 is equal to 41, alpha is equal to 1.0 times by 10 raised to power minus 5, and then we are looking for L2. That is the new length, the final length. L2 is what? Now write down the formula for linear expansivity. Linear expansivity alpha is equal to change in length, which is L2 minus L1 over change in temperature, which is T2 minus T1 times by the original length, which is L1. Now this is equal to L2 is what we are looking for, minus L1 is 3 over T2 is 41 minus T1 is 29, then times by L1, that is the original length or the initial length, which is 3. Now we know our alpha. Our linear expansivity is 1.0 times by 10 raised to power minus 5 is now equal to L2 minus L3, L2 minus 3 over L2 over 3 minus 41 minus 29 times 3. If you do this, we now have that 1.0 times by 10 raised to power minus 5. Then this will come to this side times bracket 41 minus 29 times by 3 is equal to L2 minus L2 minus 3, L2 minus 3. And so we are going to have that L2 is equal to 1.0 times by 10 raised to power minus 5 times 12 times 3, then plus 3. That is this 3 here. Coming to this side, it becomes plus. So we are now going to have that our L2 is equal to 3.0036 meters. So this is the new length of the iron rod. So this is how to calculate it. They can give you the two lengths, then the two temperature, and ask you to find the linear expansivity. They can give you the two lengths, one temperature, and linear expansivity, and ask you to find the second temperature. So whichever one they give you, put everything in the formula and use it to find the one you are looking for. It is very simple to do that. Now that you have your linear expansivity, if you want to get the area expansivity from this, you just times the linear expansivity they gave us by 2 and you get area expansivity. If you want to get the volume expansivity, you times the linear expansivity by 3. That is 1.0 times by 10 raised to power minus 5. You times it by 3, you get the volume. Times it by 2, you get the area expansivity. But for the other ones, maybe we'll solve it later.